Hello, everybody, and thank you for joining us for another Ceph code walkthrough, March 23rd, 1700 UTC. A lot of daylight saving time to standard time changing, so hopefully people make it into this one. There will always be a recording as well after we produce these, so they will be posted to the YouTube channel. And today we are joined by Samuel Just, who has been nice enough to take the time, even during the development for Pacific, to go ahead and take time to explain to us with RADOS Snapshots. I do believe, if I remember correctly, Sam, that a lot of this, back in the time, at least when I was looking at RADOS Snapshots, that was around something with a context that gets pushed around to with relation to other I/O activity that is happening. I don't know if snap context is still a thing, but of course you're the expert, so I will.
Responsibility thing.
Yeah, I think that was back in 2009. But so anyways, but I will shut up now and let the expert, of course, speak. So everyone, here is Samuel Just speaking about RADOS Snapshots. Thank you.
Cool. All right. With no particular fanfare. Okay. So I've got kind of like a presentation with some code snippets, but I've probably only got 20 minutes of content. So please, by all means, interrupt me if you want me to go deeper on something. If not, there will certainly be time at the end for questions and such. All right, so RADOS Snapshots. At a super high level, there are three Ceph projects, RGW, RBD, and CephFS. Two of these use snapshots heavily. Both RBD and CephFS make heavy use of them, RBD at a block device level and CephFS at a subtree level. But just as they both use librados, or the objector in CephFS's case, to mediate I/O, they use the same underlying machinery in librados to do snapshotting as well. So for CephFS, this looks something like this, which I stole from Greg's presentation. You can go into the .snap directory of, I believe, any directory in a CephFS tree, and any directory you make in there will, under the covers, create a snapshot at that point in time, which you can then access as a read-only copy of that subtree. For RBD snapshots, we have RBD snap commands that create list and rollback snapshots. And you can mount snapshots read-only. So the two common features here are that in both cases, we have a large related set of RADOS objects that share the same snapshot lifecycle and creation time. The two major design goals here are cheap snapshot creation and cheap snapshot reads. So at a really high level, clients maintain and arbitrate snapshot metadata for object groups externally. CephFS in its internal metadata with ordering via the MDS and capability system. And RBD maintains its snapshot information on the head object of each RBD block device with ordering via watch, notify, and locks. OSDs maintain per object snapshot to state mapping, updated with snapshot information piggybacked on writes, and I'll talk about that in exhausting detail. Rollback must be performed per object. So if we go back to this RBD example, RBD snap rollback requires time linear in the number of objects in the RBD image. Snapshot space deletion is fast, but the space reclamation part is a lazy background operation that happens across the cluster. All right, so the intuition here is that let's say we have, in this case, let's say it's an RBD image with 5 objects in it. So I guess this is a 20 megabyte RBD block device with 5 4 megabyte objects. Up at the top here, we have the client state, which currently has no snapshots. So the snapshot sequence is 0, and no snapshots have been taken. So let's say we take a snapshot. At this point, the client state now has a snapshot sequence of 3, and its little snaps vector has just 3 in it. Why 3 and not 1? Because snapshot IDs are unique and increasing, but not necessarily dense. for reasons we'll get to later. When we perform a write, the OSD is going to say, oh, 3 is greater than 0. So apparently a snapshot has happened since the last time I saw a write on this object. So I'd better make a clone. Oh, crap. This is actually wrong. I have to do it later? No. The head object here should say 3:3. That hopefully gets fixed in a subsequent slide. So let's say we take another snapshot 10 in this case. We perform a write. The left one here says head 3:3. That happened with the initial write. I just messed up this slide. So same deal here, except that in this case, instead of there only having been one snapshot that happened, 2 of them happened. So we create a clone at snapshot sequence 10 with covering snapshots 10 and 3, and the head object gets updated with a snapshot sequence of 10 with only one clone at 10. So we take another snapshot, 19 this time, and we perform a write back to the first object. So once again, 2 snapshots have happened since the last time this object was written, but this time it was 19 and 10. So the head object gets updated to a sequence number of 10 with 2 clones at 19 and 3. So let's say we need to perform a snapshot read at snapshot 3, perhaps because we've mounted this RBD image at the snapshot corresponding to snap ID 3. These read objects are the ones that will be read. If we direct a read to the first object, the OSD internally is going to direct that read to the first clone we took, and ditto for the others. At snapshot 10, we'd get these objects, and at 19, we'd get these. Note, for the objects where we haven't seen any writes since the snapshots got taken, we perform the reads at head. Do we have any questions here? This would be a good place to cut in if there's something unclear about the sort of macro structure.
I don't see any questions in chat so far.
Yep, I just figured I'd pause. Okay, so the underlying interface that RBD and SFS are using for this is the RADOS Snaps interface. There are 4 basic operations here. Snap create, which corresponds to these things where we updated the client information. Set snap write context, which also happens as part of that process. Snap remove, which is how we remove a snapshot from a pool. And snap rollback, which rolls an object back to a specified sequence number. So the snap create process is essentially a monitor operation. All that happens when you create a self-managed snapshot is the monitors give you a new snap ID that hasn't been given to anyone else on that pool, and that is greater than any snap ID you've gotten in the past. The way this is arbitrated is pretty simple. The OSD map, PG pool T structure, has a snap sequence and a snap epoch that track the most recent snap sequence number given out and ensure that we don't give out the same one twice. So every time you create one of these snapshots, we get a monitor commit that updates the maximum, and you get back the result. But at this point, no actual objects exist with that snapshot sequence number, and nothing actually has happened. Other than that, the monitor will never give out that number a second time. The second important piece here is the set snap write context. So this state in the client here, sequence 19, snaps 19, 10, 3. This is the snap write context. If you have a look at the MOSD op message that gets sent from the clients to the replicas on, right? There are 2 fields here. Snap sequence, corresponding to this seq 19, and snaps, corresponding to this 19, 10, 3. This is the mechanism by which the OSD learns what snapshots have happened on an object since the last time a write was served on that object. Within the OSD, we have these OSD level data structures. Attached to each head object is a snap set, corresponding of a bunch of fields, but the most important ones here are the snap ID T sequence, which is the highest snap sequence that object has seen, and the clones vector, which is this 19.3 thing. We also have a few look-aside structures like clone overlap and clone size that track the byte ranges that overlap between adjacent clones and the size of each of those clones. This gets encoded into the snapset attribute of the head object, and it gets cached in the OSD as a snapset context, a bit like the object context, if you're familiar with it. As we process or write, the op context has a new snapset field that projects the to-be committed snapset until the write commits. So at a high level, the OSD write path looks something like this. We receive an MOSD op from the client. We queue the op for the PG. When the op comes off the queue, we lock the PG, and then we perform some work to package it for persistent storage, mainly constructing a PG transaction. For snapshots, the most relevant bits here are finding the current object state and the execute context make writable combination, which we'll talk about in just a moment. Once we have this transaction, we send it to the replicas and to local persistent storage. But that part is after we've done the transaction bit, and it already encodes all of the information required to construct or update clones. Execute context. This gets called as early in do-op, and it is the primary entry point for the primary processing, a read or a write. Quite early in this function, if you have a look, you'll note we have a look at the get snap sequence and get snaps fields of the MOSD op. And we fill in some op context, the op context snap context, to track the pending snapshot operation, if it exists. Note, this bit only happens on mainly on write. This filter snap context call filters out any snapshots that have logically been removed since the operation was sent. Later, after we've already gone through the op itself and had a look at all of the individual operations, the last thing we do before we, well, one of the last things we do before we send it to, before we complete the transaction, is we call make writable. And what this does is it compares the snap context we constructed just a moment ago, and it compares it to the structures already on disk, as in the diagrams I showed you before. If the snap context is newer than the object, than the sequence already on disk, and has new snapshots, we create an object context with an object info T for a new clone, and we add to the transaction an operation cloning the object in make clone. You'll also notice the clone gets its own PG log entry. The PG log isn't actually aware of snapshots as such. It directly represents each new clone created with a special operation code for clone. We also encode into this log entry the set of snapshots that are stored on that clone. And if you stop and think for a moment, at the time that the clone is created, we already know all of the snapshots that that clone will be used for. Because you can't go back in time and create snapshots that happened before this point. So that set will only shrink, it will not grow. So now let's talk a little bit about snapshot removal. Deleting snapshots is also essentially a monitor operation. The OSD map contains these removed snaps queue structures that encode the total set of snapshots that are pending removal and the ones that were newly removed as part of this OSD map, or part of this epoch. Each OSD, as it consumes these OSD maps, updates each PG with a snap trim queue of snapshots to remove. There's a tricky component here, though. Because snapshots apply to many objects and not just one, we need a way to map a pool's snap ID to all of the clones within that pool that are kept around because that snap is still alive. To do that, we maintain a look-aside index in persistence on disk called the snap mapper. See source OSD snapmapper.h for more information. It gets updated online as part of primary log PG log operation, update snapmap. This snaps field, piggybacked on each PG log entry, is how the primary and the replicas all learn about these updates. When you process a PG log entry with one of these snaps fields populated, as part of the transaction being sent to local persistence, we also update the snap mapper. The snap mapper provides a reverse mapping from snapshots back to clones affected by that snapshot, which is how the asynchronous snap trimmer works. As the OSD advances its OSD map, it populates this PG snap trim queue on each PG, and asynchronously, each placement group, as the snap trim queue is not empty, will go through each of the objects in the snap mapper via getNextObjects to trim. And for each of those objects, it will check to see which snapshots are still alive, because the removal of a snapshot does not necessarily mean the clone gets removed. There may be other snapshots represented by that clone. But if there are no longer any live snapshots, the clone gets removed. And either way, we update the snap set on head with either the reduced set of snaps or with the removal of the clone entirely. The driver of this is the snap trimmer state machine in primary log PG. Reads are relatively simple. DoOp, when it is trying to work out which object to work on, calls into find object context with the snapshot sequence of the op that got sent, and it maps the snapshot sequence requested onto either the head or a clone, depending. Note that the behavior here is not dependent on the snap trimmer. Whether a snapshot that has been removed will be detected as removed whether the snap trimmer has gotten to it or not, because find object context will check the current OSD map for whether the snapshot is actually still alive or not. The last little bit of information is recovery. But there are a few important bits of recovery that have snapshot-related touch points. The first is that we need the snapset attribute on the head in order to work out which clones are supposed to exist, and some other things. So before we recover a clone to the primary, we first recover the head object. And you can see that in replicated backend recover object. Secondly, because the clone operation in object store that we use when we get a write on an object that needs to be that needs a clone created is meant to have copy on write semantics, where the underlying persistence shares extents that haven't been modified between those two clones. For that reason, it's fairly important that recovery preserve that data sharing, or else after recovery, you would find that a PG uses up more space than it should. So for that reason, replicated backend and there's analogous code in the erasure coded backend, I believe, use these calc clone subsets and calc head subsets to compute ranges of the object that can be cloned from adjacent clones that are already present. And I think that's all I've got for this presentation. Yeah. Do we have any questions? I can go into more detail. I have an Emacs window up if people have questions.
I don't see any questions listed here, but I had one in particular for myself in terms of originally I was wondering how, like, from a client perspective, if somebody was to actually be interacting with it, well, is this API actually available directly to RADOS itself to be making any sort of snapshots like this?
So there are two versions of that question. The first is no. Self-managed snapshots, as you saw, require a great deal of cooperation from the application code. So hypothetically, you could create a LibRados, an application that uses LibRados directly, in which case, yes, you could use self-managed snapshots. But the way you interact with self-managed snapshots normally is through the RBD snapshot mechanisms or the Cephs snapshot mechanisms. There is a totally separate mechanism that shares almost all of these underlying implementation details called pool level snapshots. And if you look at the Ceph documentation, I think these are even still represented. The trouble is that they aren't useful for very many things. You certainly wouldn't use them. They're mutually exclusive with self-managed snapshots, so a single pool can't use both. So if you do use a pool snapshot, you can no longer use most features of Cephs or RBD on that pool. But more importantly, even with RGW or something else or some other application, they don't behave the way you would expect a feature that has the word snapshot in it to behave, really. Essentially because they aren't point-in-time snapshots. They're somewhat complicated, and their state is gossiped along with the OSD map. So in general, that feature is fairly deprecated, I believe. Greg, is that right?
I don't know if we've actually written that word anywhere, but yeah, don't use.
There really aren't any circumstances. It would be hard to imagine a scenario in which it would be the answer to a question you're actually asking.
Yeah. Okay.
So in short, yeah, the way you use self-managed snapshots is through projects that incorporate it directly.
Yeah, the other components. Got it. Okay. Sounds good. Well, if anybody else has questions while Sam walks through the code, feel free to throw it in, and I'll try to catch Sam at the right time so he doesn't have to monitor the chat window at the same time. Thanks, everyone.
I had a quick thing. We can also cover it when you're walking through the code. Are there any quirks about snap trimming which make it different? Or is there anything special about snap trimming versus when we do regular PG deletions and stuff?
I'm not following. The two mechanisms are essentially unrelated.
No, I mean, I'm pointing this out because we've recently seen some reports of performance degradation with our BlueFS buffer IO change, which only show up in PG deletion case and snapshot trimming case.
They both cause background.
That is true, but can we categorize them as just in the same kind of work, or is there anything special about snapshot trimming versus PG deletion? Or can we just say it's the same kind of background work or not?
Snapshot trimming requires locking in PG, so that contention could be worse. But my guess is that it's if the behavior was caused by or was exposed by Blue Store level changes, my guess is that it's the IO itself. So yes, in that sense, they should be pretty uniform.
Okay, got it. Thanks.
I wasn't actually going to do any further code walkthrough. The reason why I assembled the slides was so that I could pull out the relevant bits of these functions, as the functions themselves are very long. I can pull up, is there something in particular people would like to look at? I can pull up find object context. This is fairly instructive. I didn't put this one in because it was too difficult to fit it onto a slide. The important bits here are, let's see. This OID here, this is constructed out of the components from the MOSD app. It hasn't yet been mapped to a clone. That's what find object context does. So if we scroll down a bit past the bit where, here. This covers the case that we're actually looking for the head object. This is the normal case that you perform an ordinary read or write on the object. If you're performing a snapshot read, the snap field will not be no snap. This map snap ID to clone is a special path for cache sharing, unfortunately. This part models the behavior I showed you before, where if the snapshot sequence is smaller than the sequence being requested, it's necessarily a request for head. This is the portion where we walk through the snapshot to find the correct clone for the object. It will be essentially the first clone with an ID greater than or equal, I believe, to the snapshot requested. And this portion here at the end validates that the snapshot in question actually maps to that clone by checking the clone snaps field of the snapshot. This could happen if, for instance, you ask for a snapshot that was never mapped to this particular object. Then it won't fall into that range, and you get an ANOET instead. Essentially the behavior here. We can take a little bit more look at the recovery code. There's really quite a lot to cover here, so a question got asked. Does clients need to know snapshots to talk to RADOS? How do RBD and CephFS clients get the correct snapshot info after a snapshot is created? So those questions are slightly different for RBD and CephFS. I'm going to tell a story about the way RBD works, and if Jason wants to correct me, that would be great. At a super course level, what RBD does when it creates a snapshot is it requests a new snap ID. For one thing, RBD is creating a snapshot on a block image. So it already has, I believe, a RADOS level advisory lock on the RBD head object for that image. And so the first thing it does is it asks for a new snap ID from the monitors on the relevant pool. It updates the metadata stored in the RBD head object for that image, and then it issues a notify, notifying all other users of that head object to reload the metadata corresponding to snapshots for that object. There is an authoritative updater, I believe, which is the holder of that advisory lock. The other holders will be RBD clients mounting read-only snapshots of that image, I believe. Does that answer your question? CephFS has a rather more complicated mechanism involving the CAP system. But either way, the application that is using self-managed snapshots is responsible for making sure that the snapshot information gets propagated. Though in both cases, they use LibRADOS mechanisms to do so. Does that make sense?
Yeah, it makes sense.
Cool. That's one of the reasons why there are no high-level command line ways to access this. The assumption, or the key to this system is there must already be some kind of write ordering or metadata system overlaid on top of LibRADOS. So attempting to create a snapshot level metadata would be wasteful. It's more efficient to integrate it into whatever metadata already exists.
And the clients really have to have the correct snap set to talk to RADOS, right? If they use something
Sort of.
really bad, something really bad happens, right? If they use something wrong.
That depends. If a client does not know about a snapshot that does exist, then what will happen is they obviously can't be trying to read that snapshot because they don't know about it, right? So the OSDs will see snap contexts come in that are out of date. They'll go, well, I'm going to ignore your snap context and simply give you the snap ID that you actually want. And in that sense, it will still be completely correct, right? If I ask for snapshot 5 and in fact we're up to snapshot 30, then the OSDs still know how to map snapshot 5 onto the relevant object, even if I don't know that the later snapshots exist. So for reads, it's a non-issue. For writes, there must be an authoritative writer, essentially. You won't kill the cluster-specific state. You still get a well-defined answer. Like if you have two different authoritative, or if you have two different RBD writers that are both trying to create snapshots in the same block image and sending writes to the same image, in addition to the fact that it will no longer behave well normally, you will also get sort of inconsistent. You'll get snap contexts that are different between different objects in the same image. The OSDs won't really care, but you won't get answers at the RBD layer that make sense to RBD. That was confusing, but I think the answer is, generally speaking, the OSDs won't care. For reads, the application won't care either. But for writes, the application is responsible if it wants to maintain its snapshot system. for making sure that there aren't divergent snapshot metadata floating around. To go find the calcs clone subsets here. Okay. So this is a little tough to read if you're not following along, but the idea here is that because the snapset contains these clone overlap fields, which are interval sets where any offset contained in the interval set for clone ID I is an offset shared with clone I+1 or head if it's the last clone. So by looking at the clones on either side of a particular clone, we can work out which subsets we can do a local clone range on when we're recovering the other clone. A little bit tough.
Can you repeat that?
Go ahead.
Can you repeat that?
Yeah, so this code doesn't really lend itself to going through line by line, but the notion is, let's say we have 3 clones, 1, 2, and 3. If we already have 1, 3 local, but we're missing 2, then we can look at the clone overlap field and infer, oh, clone 2 shares its first megabyte with clone 1 and its third megabyte with clone 3. That way, we don't actually have to pull that data from a replica. We can do a local clone range on those regions from the objects we already have stored locally. Not only is this a save in bandwidth from replicas and save on replica reads, it preserves data sharing between the adjacent clones at the Blue Store level, thus reducing overall space usage. So it's a pretty important optimization. This is embedded into the recovery process in general. Any other questions? Is there anything that you'd like a more granular walkthrough on?
Well, Sam, you did go over specifically in terms of being able to find an object. You went over in your presentation some of the delete operations as well as the trim operations. I don't know if those are worth going over in terms of code.
So when you actually do a snapshot removal, so let's say in RBD, if you remove an image snapshot, RBD internally is going to remove that snapshot from its own metadata and issue a command to the monitor removing that snapshot. The monitor is going to update its PG pool T. Removed snaps field, this one, I believe. In the next OSD map, as a broadcast to all OSDs that the snapshot is now removed. Those OSDs will eventually receive an OSD map in the way that OSDs always do. And activate. So, activate. Happens on activation. There's a corresponding bit of code anytime we process an OSD map. I'm forgetting the location of, where it initializes the snap trim queue and the purge snap set. As long as these things are not empty, there's a background operation called the PG, or the primary log PG snap trimmer. The main state, it's structured the same way the peering state machine is with one of these boost state chart state machines. The initial state is unsurprisingly not trimming, and the other states are trimming, whereby it's going one object at a time through. And let's see if I can get the more important one. The wait trim timer state, I believe, is where it's waiting for there's a configurable that adds an artificial delay between different operations, between drum operations in the background, in this background process. I believe that's modeled by this wait trim timer state. Wait RW lock waits for getting the right lock on the objects that need to be trimmed, specifically on the head, I believe. Wait rep ops waits for the replication operations to complete on the replicas. A trim operation is essentially identical in structure to a client write or any other logged operation. Just as with a client write, we create log entries and send PG transactions and log entries to the replicas. So recovery and failure work the same way as with a normal write. Actually, not sure what await async work does. I believe await async work waits for the local operation to complete. Might actually be new. Wait reservation, I believe, is waiting for a reservation on OSD resources so that we don't have a whole ton of PGs doing snap trimming at the same time. Wait scrub is a relation between this and scrub, where if we're currently scrubbing the PG, we need to wait for the scrub to complete before we can continue.
We are waiting on per object or for the whole PG?
This I can't remember. Let's go find out. It looks to me like we're waiting for scrub to complete.
Okay.
I'm grepping for it. It looks like you want to grep for snap trim or scrub complete.
Yeah, I will do that.
Which gets called in PG scrubber. And we call it on scrub finish. So yes, on scrub completion.
So another question that gets brought up at least with the Ceph boost at various events is around RBD mirroring. And as I would like to understand, this is probably an after event thing, after all these contexts are set and done. Is that correct? RBD mirroring would just be pushing out to whatever other sites that would be available? The snap context?
I am going to make some wild guesses that Jason can correct if I'm wrong.
Okay.
I believe the way snap mirroring works is RBD periodically takes snapshots and it mirrors those snapshots over. It then uses the RBD intent log to update the current version of the block image on those sites up to the current state of the current image. So it uses snapshots as one of its components, but most of it's RBD level. Does that make sense? That is, RBD itself maintains, I believe, a write-ahead log of sorts for its for mirroring purposes, and the remote cluster consumes that log to bring itself up to a point in time consistent state, time delayed by some amount, but it's not directly a function of snapshotting. It's just one of the subcomponents.
Yep, that makes total sense. Just wanted clarification on that. Also looks like we had Jason for a second, but he's not on right now.
Oh, well, take that with a grain of salt then. I think that's
Yeah.
correct, though.
It sounds about right to me. I mean, back when
is that snap mirroring is for disaster recovery, so I think it is just synchronizing the snapshots.
Oh, I see. Okay, then that's even simpler.
It does them as frequently as like the pipe can handle the updates, but you just take a snapshot.
There was also an intent log though.
Well, there's also the full data logging mirroring version.
I see. I didn't realize that that's what that term specifically mentioned.
Yeah,
Got it now.
The snap mirroring is a lower cost one.
Got it.
Thanks, Greg.
Yep.
And I guess amongst all the different components that Ceph has, are there any limitations in terms of one component to the other in terms of snapshot features that you are aware of?
I mean, yes. Like Ceph's snapshots don't really resemble RBDs, right? It's built on the same substrate, but they're really different. As an example, all of the objects within an RBD block image will all have the same snap context, but that's not true of all of the objects in Cephs. A file in Cephs can be contained in multiple snapshot domains, I believe they're called, Greg. That is, if you snapshot its directory, its parent directory, and its grandparent directory, all at different intervals, then the objects in that subdirectory will have the union of all of those snap IDs. From the point of view of the way self-managed snapshots actually work, this is irrelevant. It doesn't actually matter. But the way the feature is used makes Cephs' snapshot features wildly different from RBDs. Does that make sense? I guess snapshots are integrated based on the way the component or based on the way the external interface actually works.
I think the more interesting one is when you move a file out across directories that have completely separate snapshots, like patterns within them. So a file that was in my directory getting snapshotted for like a month, and then I gave it to you, and so now it's in /home sjust, and it's getting your snapshots, but it's also still in my old set, but not my new set.
I forgot about that one. But the point is that, yes, the features are different. Because the actual, everything about Cephs is quite different from RBD.
In terms of snapshots shortcomings, I think the big one is that these are read-only. There are some storage systems where you can take snapshots, but they're not, but they're writable, so you can actually just have like different branches of versions of the file. And people ask us for that one pretty often, and we'd have to completely redo it.
Honestly, the only local file system I'm aware of with that feature is ButterFS. And it's not a well-liked feature.
Filers do it. Not filers do it.
Oh, really? Ooh.
Yeah. And I think a bunch of...
But that's not a feature differential between different interfaces and stuff itself.
And virtualized desktop environments are a big fan of it.
Yeah, I was going to mention that as well. There have been a handful
Actually,
of
RBD does have that feature after a fashion. Now that I think about it. They're not snapshots. It's not built on top of, well, it's not exclusively built on top of them, but you can create thin, what do they call it? Sparsely provisioned copies from a parent image.
You can clone a parent image.
There we go. So RBD does have that feature after a fashion.
I think another thing that we could talk about, because one of the moments for Ceph was of course during when OpenStack was first coming aboard, and there was a need for shared storage, having a way to give storage to different virtual machines at the beginning. Maybe you could kind of talk about the cloning and snapshot on that with RPD as an interest point.
So same basic concept. I'm gonna tell some high level, probably truths, but probably not strictly accurate. So at a super high level, an RBD image is a set of RADOS objects. The simplest version, and I believe the default configuration, is where you simply divide up the image into 4 megabyte chunks, and each chunk is its own RADOS object. So a really simple way to create, let's say you have the sort of classic example of you want to create a base OS image, let's say for rel whatever, and you want customers of your cloud deployment to be able to quickly spin up new VMs based on this rel image. So you take a snapshot of the rel image, and then you create a new block image with that rel snapshot as a base. And what that means is that RBD maintains a bitmap of all of the blocks that actually exist within itself. And anything that is not in that bitmap, it passes through to the parent image. In this case, the clone that was the original rel image. And every time you do a write, it copies up and I believe that's the operation of the librd source code. It copies up the parent image's 4 megabyte block up into the child image's layout, and updates the bitmap to ensure that all future reads will hit that block instead of the parent one. In that way, you get this kind of thinly provisioned behavior where you don't actually create a new image. You just create new blocks corresponding to the things that have been mutated since you created the image. So just as with the mirroring thing, it makes use of snapshots, but most of the behavior is actually RBD level. That I am not familiar enough with to find the source code to, though.
That seems about right from how I try to explain it to people as well. So,
and I'm pretty sure it's a bitmap. I think it's pretty just basically maintained on the head object.
Great. Well, I wanted to also check to see if anybody else wanted to speak up with questions as we are approaching the end of the time for the code walkthrough. Okay. Sam, was there any last things that you wanted to share in terms with RADOS Snapshots?
No, I think that's all I have. I hope that was useful.
All right. Well, great. Thank you, everybody, for joining us for another Ceph code walkthrough. And as I mentioned before, this will be posted up on the Ceph YouTube channel. While I have everybody's attention as well, I wanted to make a note that the Ceph release shirts for Octopus have gone out. Design for Pacific is on the way. Everybody's hard work on the next Pacific release for this month. And lastly, we have the Ceph user survey that's ending April 2nd. So please fill out that survey when you can. I can put it into chat real fast. But otherwise, we have another tech talk that is coming up, and it will be on the 25th. So this week, and we'll be having specifically a presentation on bucket persistent notifications. So invite everybody to join us for that. That's at 1700 UTC. And there'll be updates on the Ceph mailing list and Twitter as well. So thank you, Sam, again for taking the time to go ahead and walk through with us on RADOS Snapshots and answer our questions. And we'll catch you all next time for the next Ceph code walkthrough next month.
Thank you.
Thank you.
Okay. Have a good one, everyone.